The Unity Performance Checklist, born from 20 projects and countless mistakes. Hello and welcome to episode number 16 of the Unity Performance Task Force podcast. I'm your host, Ruben from TheGameDev.Guru, and today I want to share something a bit different with you. Instead of diving deep into one technique, I'm going to walk you through the Unity Performance Checklist, a document I've been refining for years, built from real scars earned across more than 15 commercial Unity projects. Let me kick things off with a question for you. Have you ever fixed a performance problem in one project, then completely forgotten about it in the next one? Maybe you spent hours tracking down a culprit, finally solved it, then 6 months later on a new project, boom, same mistake, same profiler spike, same frustration? If so, this episode is for you. The story behind this checklist is simple but humbling. After my first dozen or so Unity projects, we're talking mobile games, VR experiences, PC titles, I noticed a pattern. I kept making the same optimization mistakes. Not because I didn't know better, but because there are so many things to remember between projects. You finish one game, move on to the next, and suddenly you're back at square one, profiling the same bottleneck you solved a year ago. I'll never forget the time I was debugging a camera clear flags issue. I googled it, found the Unity forum post with the perfect answer, clicked through, and realized the person who solved it was me, 3 years earlier. That was my wake-up call. So I started building this checklist. Every project, I'd add new items, refine old ones, and capture the lessons I didn't want to relearn the hard way. If it saved me time, I figured it might save you time too. That's why I'm sharing it with the Performance Task Force community, and that's what we're unpacking today. Now, before we dive into the checklist itself, let's talk about the big picture. Performance optimization in Unity breaks into 3 main pillars: CPU, GPU, and memory. Today I'm going to focus heavily on CPU optimization, specifically rendering, because in most projects, especially VR, rendering is your biggest cost. When I was working on Star Trek for Quest, rendering ate about 60% of my CPU budget. 60%. And this is typical for VR, where you're preparing draw calls for both eyes, hitting 72, 90, or even 120 frames per second. The math is brutal. If you're targeting 90 Hz, you've got roughly 11 milliseconds per frame. If rendering takes 6 or 7 milliseconds, you've barely got time left for gameplay, physics, or AI. So let's talk rendering. Most of your CPU rendering cost comes from preparing draw calls, the instructions Unity sends to the GPU saying, hey, draw this mesh with this material. In theory, you'd issue 1 draw call per renderer in the scene, but that would be way too expensive. That's why we have batching. Batching groups draw calls together based on shared properties like materials and shaders. And here's the first big lesson from the checklist. Keep your shader variant count low. Not just the number of shaders, but the number of shader variants. If you've watched my video on shader variants, you know Unity can silently explode one shader into dozens or hundreds of variants based on keywords, lighting settings, and features you didn't even know you enabled. If you can keep shader variants low, you've won about 70% of the battle. Next, minimize your material count. Do that and you're at 95%. These 2 steps, fewer shader variants, fewer materials, are the foundation of efficient batching. Now, here's where it gets interesting. The advice changes depending on your render pipeline. In the built-in render pipeline, draw call count is king. Every draw call has significant overhead because Unity has to bind parameters, submit buffers, change GPU state, then unbind and repeat for the next call. It's expensive. But with the scriptable render pipeline, that's URP and HDRP, things work differently. The SRP Batcher keeps constant buffers on the GPU across frames. So even if your draw call count stays the same or even goes up, you're sending far less data per call. The overhead drops dramatically. This means draw call count is less critical in URP than it was in built-in. You still want to batch efficiently, but the panic threshold is higher. There's a wrinkle here though. As of this recording, there's a known bug on OpenGL ES3 where the SRP Batcher breaks on Quest. It's been discussed in the forums and Unity is working on patches. If you're developing for Quest on URP, check your Unity version. The fix is rolling out in incremental releases like 2021.1.16. If you're hitting this bug, your best bet is to profile with RenderDoc or Frame Debugger and confirm whether batching is actually happening. One question that came up during a live session was about Vulkan. Oculus now supports it, and Unity's been talking about it for years. Should you switch? The short answer? Maybe, but test carefully. In my own experiments and conversations with colleagues, we've seen about 20% CPU improvement with Vulkan over OpenGL ES3. That's not trivial. But Vulkan is finicky. If you're deep into an existing project, switching can break things in subtle ways. My advice? Try Vulkan on new projects from scratch, fix issues as they arise, and don't assume marketing benchmarks apply to your specific game. Always profile your own build. Let's shift gears to UI. Unity's canvas system is powerful, but it's also a common performance trap. The classic mistake is having too many canvases. Each canvas has fixed overhead, but the opposite extreme, one giant canvas, also causes problems, because anytime a single element changes, Unity has to rebuild the entire canvas. The sweet spot is grouping elements by update behavior. Static elements go in one canvas, dynamic elements that change together go in another, elements that update at different rates get separate canvases. I once optimized a project from 20 canvases down to 8. The gains were huge, but it took time, because I had to analyze which UI elements changed together, then restructure sprite atlases and hierarchies to match. If you're on mobile and limited to 2K atlases, this gets even trickier. UI optimization can easily eat weeks if you're not careful. Another tip from the checklist: avoid world space canvases when you can. Now in VR you're often stuck with them, but on flat screens, world space canvases tend to multiply out of control. Developers attach one canvas per character for health bars, another for damage numbers, and suddenly you've got hundreds of canvases. Screen space canvases force you to consolidate, and if you write custom UI shaders, especially opaque ones that support early Z rejection, you can cut overdraw by 80%. I've done this multiple times. It's easier than you think. Let's talk particle systems. One developer asked me about memory consumption from thousands of particle system instances. Particle systems are expensive because Unity keeps them generic. The system doesn't know what you're trying to do, so it retains flexibility and overhead. If you've got thousands of instances, consider converting particle effects to mesh renderers or sprite renderers animated via ECS or dots. You'll have tighter control and lower memory overhead. Another technique, which I'll cover in an upcoming video, is rendering a particle effect once to a texture, then reusing that texture as a sprite across many instances. It's the same trick used for character imposters, and it works beautifully for repeated VFX. Now here's a curveball: skyboxes. Oculus documentation has historically warned against skyboxes, and many developers assume that means never use them, but the real issue is render order. In older Unity versions, the skybox was rendered first, before opaque geometry. That meant massive overdraw. You'd draw every pixel of the skybox, then overwrite most of it with your scene geometry. Total waste of bandwidth. In modern Unity, the skybox is typically rendered after opaque geometry, filling only the pixels that aren't already covered. That's fine. But if you want ultimate control, create a custom skybox using an inverted sphere or dome with your own shader. You can optimize texture sampling, control when it renders, and even punch holes in the geometry if certain areas are always occluded, like in a cockpit view. Specific knowledge always beats general-purpose systems. Anti-aliasing in VR is another pain point. MSAA is your friend on mobile and Quest, but enabling post-processing in URP can break MSAA. If you're relying on post-processing just for color correction, there's a better way. Quest has a color space API you can call from script. I've seen developers use this to match editor colors to device output without the overhead of a full post-processing stack. If you absolutely need screen space effects, consider faking them. Want a damage vignette? Instead of a post-processing overlay, tint all materials in the scene red for a split second, or render a mesh with an inverted normal cone around the camera with a custom shader. It sounds hacky, but it's way cheaper than a full screen pass. Here's a quick one from the checklist. Use object pooling. If you're instantiating and destroying objects every frame, projectiles, enemies, particle systems, you're hammering the garbage collector and fragmenting memory. Pool those objects. Spawn them once, reuse them, and disable them when done. This is standard practice in professional studios, and it should be standard practice for you. Another tip: cache everything. I know, it's annoying. Your code balloons with cached references to transforms, cameras, and components, but the alternative is fetching them from memory over and over, and that adds up. In big projects I've worked on, we cache aggressively. Sometimes 60 lines of a 200-line class are just cached references. It feels ugly, but it works. If you find yourself resisting this, automate it. Write editor scripts that generate caching boilerplate for you. You'll thank yourself later. Let's talk about a subtle one: set active and enable calls. Developers often wonder, If I call setActive true on an object that's already active, does Unity skip the work or does it do it anyway? Honestly, I don't have a definitive answer off the top of my head because it's changed over Unity versions. But here's the broader lesson. Measure it. Create a test scene with hundreds of objects, toggle them on and off, and profile the difference between calling setActive unconditionally versus caching the state and only calling it when needed. That's the skill that matters more than memorizing trivia. If your code fills up with state caching if statements, weigh that complexity against the performance gain. Sometimes the cleanest code wins. One thing to watch out for, setActive on UI elements is expensive. Unity has to traverse the hierarchy, fire onEnable and onDisable on every component, and recalculate layouts. If those components include animators or UI elements themselves, the cost compounds. Measure carefully, and if you're toggling hundreds of UI objects, consider restructuring your hierarchy or using a different approach like alpha twinning or moving objects off screen. A related tip from the checklist, use the transient pattern. If you're not familiar, it's a way of structuring your objects so that expensive setup happens once, then you reuse the object by resetting its state rather than destroying and recreating it. It pairs beautifully with pooling, and it keeps your frame time smooth. Here's something that tripped me up for years, deep profiling. Unity's deep profiler is amazing for finding bottlenecks in your own code, but it slows your game to a crawl and can give misleading results. Use it sparingly, in controlled tests, and always cross-reference with non-deep profiling and platform-specific tools like RenderDoc, Xcode Instruments, or Android Studio's Profiler. Deep profiling is a flashlight in a dark room. It shows you where to look, but you still need to verify what you find. Another subtle one, reflection. Calling gas-kimtomt, sebsindent, or using reflection-heavy APIs every frame is slow. Cache component references in awake or start. Use direct references instead of string-based lookups. And if you're using a dependency injection framework, make sure it's not doing expensive reflection at runtime. This is one of those 1% per call costs that adds up when you're doing it thousands of times per frame. Let's close with a few quick hits from the checklist. First, avoid excessive hierarchy depth. Unity's transform system has to traverse parent-child relationships constantly. Deep hierarchies, especially in UI, slow that down. Flatten where you can. Second, if you're using animator controllers, watch your state machine complexity. Tons of transitions, layers, and blend trees can bog down the CPU. Profile your animators separately and simplify where possible. Third, if you're on mobile, be ruthless about texture sizes and compression. A single uncompressed 2K texture can blow your memory budget and tank load times. Use ASTC on mobile, BC7 on PC, and always profile memory usage on device, not in the editor. Okay, let's bring this home. The Unity Performance Checklist exists because game development is complex and memory is fallible. You will forget things between projects. You will make the same mistake twice. That's human. The checklist is your safety net. It's not about being perfect. It's about having a system that catches the common stuff so you can focus on the hard, novel problems unique to your game. Here's your action plan. First, grab the checklist. Go through it once, slowly, and flag the items that apply to your current project. Second, profile your game right now. Don't wait until you're 2 weeks from launch. Find your biggest bottleneck, CPU, GPU, or memory. Third, apply 1 or 2 fixes from the checklist that target that bottleneck. Measure before and after. If you see a win, great, document it. If not, dig deeper. And fourth, make the checklist your own. Add items specific to your game, your team, your platform. This is a living document, not a stone tablet. The checklist I use today is the result of dozens of projects, hundreds of mistakes, and thousands of hours profiling. But it started with a single frustrated Google search where I answered my own question. You're not going to remember everything, and that's okay. Build systems that remember for you. If you found this podcast episode useful, you can access in-depth lessons in the Unity Performance Task Force program at www.performancetaskforce.com. And if Unity Consulting is what you are after, book a free discovery call at https://consulting.thegamedev.Guru. Till next time,